better known as Richard.
Yeah, it's better call me Richard. I don't want to get into trouble.
And the title of this talk is Discovering Modular Data from Congruence.
So thank you for the invitation. This is the second time I visit the NCSU actually. The first time was 20 years ago, some meeting organized by me. But I barely remember this place.
No, this was not there at that time.
Yes. Okay, so today I will talk about this joint project with Eric Rowell, Zhenghan, Wang, and Xiao-Gang, Wang. This is joint project is about discovering modular data. So you may not realize why do you want to do that? What's the point? I mean, so Chelsea actually gave an introduction yesterday. There is application to conformal field theory, TQFT, and quantum computation. But these are big words. But like today, I just want to show you with some application and how I enter to solve some problem and find the modular data by using representation as a 2C. So the modular group play a big role here. We are not number theorists, but this is actually the favorite group of a lot of number theorists. There are two groups. One is this group, the other one is the absolute Galois group. This group is certainly one of them. So as a SL2C, just the 2x2 integral matrix of determinant 1. It has a presentation. So this presentation is actually given by the matrix. This is, let's say, the order 4 inversion. The other one actually is a horizontal translation by unit 1. So you can write down the generator relation with it, which is like st raised to the power 3 equal to s squared. This is just one presentation. There are others. So the other one is s4 to the 1. So these two basically is a generation, the presentation of the modular group in abstract terms. So if you have two matrices, which is one is called big S, the other one is big T, then they satisfy these two relations. Then you can write down a representation for this group. However, every time you define something using the generator relation, you do not know what it is in general. You can define something quite immediately, but you don't know what it is. So let me just tell you something general. So if you have a representation, just ordinary representation of SL2C, we call it congruence. I just borrow the word from people in theory. If it factor through this finite modular group, so for some positive integer n. The other way to say it, maybe this is actually the time to introduce some notation. This is the gamma n, which is the kernel of this reduction. This is the objective one. So this is the principal. So usually we call it principal congruence subgroup level n. So basically, the kernel of the representation contains some of these congruence subgroup. This congruence subgroup is very rare in the subgroup among all the subgroup SL2C. Majority of them are non-congruent. Very few of them are congruent. Very few. So you can see why it's very special if you have a congruent representation. So, but you can easily see that if the representation completely determined by the image of I call it small s, which is the image of the flag s, and the other one is small t, which is the image of flag t. So these two matrices completely determine the representation. So I generally call these pair S and T matrices, but in a loose sense. Now maybe I just stop a little. So because this group has to be used forever, so I need to have any question here? No, then I move on. So now I
maybe one.
Yes.
Do you intentionally call them S and T, as in like?
Yeah, I just always use S and T to stand for the image of S or image of T. But maybe S tutor, maybe capital S, they all reflect this image of S.
I mean, like as the ST matrices, so like an MTC.
Not necessarily.
Okay.
But they're related. So now actually the original motivation and also the application that I'm happy to have. So associated to a rational conformal field theory, let's say it's given by a nice vertex operator algebra. There's a representation SL2C. This actually usually come from the so-called modular invariance of the conformal characters. So the number R is the number of irreducible or simples, or sometimes in physics literature they call it primary fields. So you pick a homogeneous element V in V of degree K, and you pick a simple module M, you can define a meromorphic function, define all the Hubbard plane. So each simple module give one. So now this is a famous result of Ju. You take all the irreducible of V, and then you write down the corresponding, take a V of degree K, and you write down the corresponding character. Then they satisfy this transformation. So this the one that I hear is if you take a matrix A, B, C, D from the modular group. Oh, I should use the other. From the modular group, why they doesn't change color? Okay. I want to pay attention to this. This matrix applied to tau, basically the Fourier transform. Then you get your linear combination with this factor, C tau plus D raised to the power K, this K actually reflecting the weight. And then times a matrix gamma ij times this character. So that means these character vector function give you a representation of SL2C. Moreover, they are actually weight K vector value modular form. So then from here you can study the number theoretic property of a VOA, but you can also study VOA by itself. So you can have more than one direction. Now these character has been out there for decades. So there was some open problem, which is that these characters are actually congruence modular form. So what happened is if you have a congruent modular form, the Fourier expansion of the congruence modular form, the coefficients are algebraic integer up to a scalar. This is actually an arithmetic consequence of being a congruence modular form. So what we can prove by using a modular tensor category is that these representation SL2C coming from a vertex operator algebra is indeed a congruence representation. So then you may ask what's the level? The level is given by the order of the T matrix. So this is one of the application. So we actually solve this problem. Now, any questions?
So you're nicely knowing it's rational.
Well, you can say it's like strongly regular. Then if you put a bunch of words there like self-dual, C2 cofinite, simple. And then sometimes you may want, if you look at the Huang's paper, sometimes you refer to those conformal weight are bigger than zero except the vacuum. That one will give you I will talk about the later, the dimension there will be all positive, the categorical dimension. So it all comes back to a result of Lapowski and Wang. So this VOA gives you a very nice category, which is the modular fusion category that I allude to. So basically, we derive result of general modular tensor category and apply to this VOA module category. We get what we solve. There are more. In fact, we solve a couple open questions in the same paper with Don and Lin. So in general, associated to a modular fusion category, like I just specified, the modular fusion means the underlying category is semi-simple. In Chelsea's talk, the underlying category is non-semi-simple in general, but include the semi-simple one, of course. So I just focus on the modular fusion one. And there's a braiding. Braiding is a natural isomorphism to switch two objects. A and B here, the small a, small b, I mean the simple objects in the category. So let me just we usually write a braiding this way. I read it from the top to the bottom. But it never mattered actually. So like if they have a braiding and then they have something called a twist or a ribbon structure, which is a natural isomorphism. And then Chelsea alluded to yesterday. I don't want to use theta here because I want to reserve it for the scalar associated to it. Maybe I use omega here, ribbon structure. So maybe that's just a good juncture to say the ribbon structure is in one-to-one correspondence with the spherical structure. If you fix the braiding, there's a correspondence there. So that means like if you fix a ribbon structure, you get a way to take the trace. They are corresponding. You cannot pick other spherical structure. You hope to get something nice. They will be off a little. So there's you fix the braiding, then these two structure, ribbon structure and spherical structure are in one-to-one correspondence. If you fix a spherical ribbon structure, you have to use the spherical structure to compute trace. So if you look at it, I have two things there. One is the braiding. I cannot take the braiding, the trace for the braiding because the domain and codomain are different. So, but if I choose the double braid, then the domain and codomain are the same. So if I braid again, so then, well, the spherical structure basically allows me to close it. Without that, I cannot close it. So I don't draw the stars. So you can also, because it's spherical, you can actually do something slightly different. So I think many people know that this picture means like from 1 to 1. So it represents a scalar times the identity of the unit object. So we just pick out the scalar. So we consider this is a S, maybe I call a star here because this is convention, AB. It's just this scalar. The other one is, I call it theta A, but it's given by, this is a morphism times identity of VFA, A simple. AB are simple objects. So because like, it's a simple object, it's a scalar times identity, maybe I use identity to measure. Pick out the scalar. So I just show you what S matrix is. So the T matrix now, so the T matrix is written there. So we just repeat it, T matrix given by this delta AB. This is the delta function, theta A. So now I have two matrices. One is big S, the other one is big T. As I mentioned before, they're related to the modular group, the inversion and the translation. So the next line basically tell you the relation. If I take the modular group, I assign the inversion to the big S. This is the matrix I just defined. And the big T, small t go to the big T. I don't get a representation here. I get a projective representation. That means there's a factor of. So for those people who work on TQFT, actually this is the mapping class representation of the underlying TQFT of this modular tensor category of the mapping class group of the torus. So you can get the same thing. It basically is the representation of the mapping class group of the torus. So you can get it from the topological picture, you can get it from the algebraic picture. So for example, in Chelsea's talk, he mentioned about non-semi-simple like modular tensor category. You can also build some kind of TQFT, but not with the category. That means you also have some S and T matrix associated. You just get the representation of mapping class group instead of going through the category. So you do, even in semi-simple case, you have some S and T matrix playing around. So this is not an ordinary representation, just a projective representation. Everything is off by a scalar. So okay, but this is SL2Z, you can lift. You just rescale this matrix. Then I call this lifting. So technically, you just do this, you just raise it. So I just have this representation. This is projective one. I say this is SL2C. You have a GL. R. This is rank. But you can go to the projective one by just forget about the center or modulo the center. And this is my row C tutor. This is my projective representation coming from the category. Whatever lifting basically means when I rescale, that means I have ordinary representation. I project to the projective general linear group. I just get a diagram there. So there are not that many of them. There are not that many lifting. So basically, just rescaling. If you look into the matter, there are not many ways to rescale the representation. So what we actually prove is the following with Dong and Ling. So every lifting of this projective representation of the modular tensor category is a congruence representation. And in this case, in the case of VOA, the representation SL2C coming from the modular invariance actually is a lifting of the underlying modular tensor category. That's how we complete this application with the theorem in the context of modular tensor category. So this gives you a reason for us to pursue further. In fact, I have more application down the road. So this is a Jones conjecture before he passed away. It's actually when we were in MSRI, he broadly emphasized this open conjecture. Basically, is that every modular tensor category can be realized by a VOA. That means, so how does it do it? Nobody knows, but there's some progress by Terry Gannon that you can do it for the twisted quantum double. Except that you realize the underlying VOA is not an orbifold, it's not a holomorphic orbifold, or we do not know the underlying VOA is a holomorphic orbifold. So this question actually is another driving force to bridge so-called quantum symmetry together, given by term by Chelsea. So you basically join the people from subfactor, half algebra, VOA, and this quantum computation together to build a network of mathematics. So my entry point of this talk is basically how can we reverse this representation. So you have a representation obtained by lifting the projective representation of modular tensor category, and hence you give a character of the finite modular group. This is a finite group, so they are completely determined by the character. So can we reverse it? That means like if you give an arbitrary character of finite modular group, can you regenerate or discover or rediscover that the original modular data? Well, looks like it's a pipe dream, and I did not believe it could work, but it works. This is a surprise. The surprise is it works. We can find the reverse engineering from. Is it a full? Is it a complete description of the original one? No, but what I get is the Galois conjugate of the original one. So in modular tensor category, you can do the Galois conjugation. In VOA, it's not the case. So you start with one, you compute the representation. If you take the character and regenerate it, and you get the Galois conjugate together with it. So so this is basically the second question. Is the one that what we're going to pursue the investigation. So how does it work? I mean, basically we have to look at the arithmetic rigidity of this modular data. In fact, there are a lot. So let me just come from something which is known for a long time ago. So take SNT to be the modular data of an MFC, which is just defined, not rigorously. But I hope all you get some idea. There's some two matrices, they looks like they decay the representation. But they are not just ordinary representation. So the length of this matrix, so this is a symmetric matrix, S matrix is a symmetric matrix. And the length of each row or column are the same. So I just simply define the dimension in this way. Nobody defined this way. Because for this top, I just define this way. So length is just defined in terms of the length of the S matrix. The square root of the length is this square root of the dimension. Just to say, the square root of the norm square of the length. Norm square is of each row is the dimension of C. So the first arithmetic rigidity is the famous Verlinde formula. It's not. So you take the S matrix, and then you do this kind of arithmetic multiplication, division. Looks like it's ridiculous. And then you sum them all together. This sum is over L. L is all the simple object. And then here I use divide out the global dimension, the dimension C given by the length of the row. This is the fusion coefficient or the multiplicity of the k simple object appear in the tensor product Vi tensor Vj. So of course it's an integer, non-negative integer. But look at the left side, the right side. The left side is a non-negative integer. The right side is a bunch of complex number. So this is a miracle here. So this is actually a arithmetic rigidity. You don't have an arbitrary matrix satisfying this. So I usually call Nijk the fusion rule. I just follow the physicists. Just call fusion rule. But here it may be called multiplicity, whatever name coefficient. I just call it fusion rule. So now I get this is the first. This one was known for a long time actually. Somehow the knowledge descend to the notion of modular tensor category. And the first few arithmetic rigidity actually observed by those physicists actually. Maybe I just reverse all a little bit. Maybe if you look at this line, it's actually discovered by them. If you take the Sij over S0j, when every time I do put 0 there, which means the row corresponding to the unit object, because we are talking about tensor category, there's a unit object involved, the unit object symbol. So it's always one of them. So the S matrix is indexed by the simple object. I just take the row decided by the unit object. So you take the Jth row and take the first this unit row, and then you divide out the coefficient. They're always algebraic integers. This one is already a rigidity. And then Zhenghan and Eric actually proved further that if you take the global dimension, take the square root, divide out S0j. Now this means S0j has to be non-zero. In fact, they're real. It's a result of the paper of ENO, Eric of the Mixed and Ostrich. It's real. It's a real number, non-zero number. And you divide out again. Again, it's an algebraic integer. So you have two numbers divided is the algebraic integer. Now the Galois group, another Galois group kicked in, which is the absolute Galois group. This is these two groups actually is interesting number theories rather than us. So take a sigma to be the absolute Galois group. So the S matrix actually give you the character of the fusion ring, of the fusion rule. So because of that, the quotient actually the coefficient which is inside the character of the fusion ring. So therefore, because the matrix ring is an integer, so the eigenvalue are all algebraic integers. So therefore, the Galois group will act. And you take a Galois group, you can only move one character to the other. They just permute them. So therefore, you have a natural permutation from the absolute Galois group to the object, the simple object of the modular tensor category. This one is probably not known in the VOA body before. So because we completely look at it from the point of view of category theory. So my entry point of this kind of result is I work on half algebra before, and then I start to work on invariant of tensor category, and somehow we discover some invariant which allow us to push a lot further than what we know. So if you look at the S matrix, in fact it is a matrix of cyclotomic integer. You divide is still integer, but itself is already a cyclotomic integer. Actually, there is a cyclotomic integer inside the cyclotomic field defined by the order of the T matrix. So they all related. So in particular, this quotient that we talk about discovered by the physicists, actually they're cyclotomic integer living inside the cyclotomic field defined by the order of T. This one was an open question. They did not know. They did not know what field they sit in. Well, we know. So we have another theorem which is relate how you relate the dimension and the order of t. So you take the global dimension, this is an algebraic integer, because as a you can take norm, or you look at the minimum polynomial, look at the constant term, which is an integer, and order of t is another integer. You have two integers, they look like they're unrelated. No, they're related. So you prime factorize them, then the prime factor of them are the same. So the dimension, the norm, the prime factor of the norm of the global dimension is the same as the prime factor of the order of t. So this is actually a generalization of the Cauchy theorem. So we simply call it Cauchy theorem. You may not see why it's Cauchy theorem, but I don't want to spend time to explain why. But this is an arithmetic rigidity that is actually appear in the modular data. Now, this is all modular data at the moment. So now I can lift to the ordinary representation. This is only gives you a projective representation. I want to lift to the ordinary one. Now the ordinary have even more geometric symmetry. This is something that we did not expect, but it's also inspired by the people in rational conformal field theory, particularly Terry and Gannon and Cox, I think. So looked at like S and T are S is symmetric matrix, T is a diagonal matrix. This is the way I define it. So when you lift them, they still symmetric and diagonal. So and moreover with the lifting, they're all unitary. So I specific call this kind of representation symmetric representation. So that means I have a representation SL2Z, the image of S is symmetric, and the image of T is diagonal. How often it could happen? In fact, it happens for all congruence representation. But when it's not congruent, it may fail. So I suspect in non-semi-simple theory, you don't have a symmetrized representative. So to cut the language short, I just simply call the lifting of this projective representation of SL2Z coming from modular tensor category. I call it row tutor bar. Any lifting, I just call it MD representation. Basically mean modular data representation. It completely derived from modular data. There are more than one. So the next line, I just tell you that, okay, if you don't get something different, they're not too bad. They just differ by a character of SL2Z. But we know the character. I mean, when I say character, I mean one-dimensional character of SL2Z. The one-dimensional character actually form a group of order 12, which is cyclic. So that means the character at most can change the root unity by a group of order 12. So if you know one lifting, then you know all others. But you don't know which one. For the VOA, actually completely determined by the central charge. It's not something that is arbitrary. So this is another theorem in the same paper. So this actually solves another question of Terry, Gannon, and Cost. he discovered this relation a long time ago. If you apply the Galois group, at that time they don't know finite. That you apply absolute element, the absolute Galois group, to this matrix of algebraic integer, you only change by a sign permutation matrix times the original representation. They know it a long time ago, maybe in the 90s. They know it already. What they did not know was this one actually has a formula. In fact, he write down a conjecture in his book, Monster, Moonshine. He conjectured actually this sign permutation matrix is given by this formula. In fact, it is. So moreover, if you use the Galois group twice acting on the T matrix, you just permute the diagonal. So how do you permute it? Remember that I told you at the beginning, the Galois group actually introduced a permutation of a simple object, exactly this permutation. So they all fit together perfectly. Now this too was unknown, but actually you can solve generally for any modular tensor category. That means every lifting will satisfy this property. So in particular, in the case of VOA, you get this particular one to satisfy this. So this actually become a arithmetic rigidity now. It's no longer it's a result, but remember it works for all modular tensor category. It all satisfies this. So it become a constraint for modular data and the underlying lifting. So the point is, can we use it to solve? If I give you a character of the representation SL2 Z mod NZ, can I use it to solve the original modular data? This is the the part that I did not believe it can be done, but actually it can be done. This is why I give a talk here. So I call it mining for modular data. So we do mining in Bitcoin. So this, to me, is more valuable than Bitcoin. so we are mining for it, basically. You go to the ocean, look at the sand, and then you look for you want to mine for something precious. So the input actually is characters of finite modular group. This is the input of the machine. This is my mining machine. So I want to draw the picture here because I really like this machine. So I have a machine. This is not a very. So this is my mining machine. So the input actually is a character of SL2 CMOS NC, and the output I want is modular data. So if you don't get anything, you get empty set. If you get something, you spell it out, all of them. So this is my mining machine. I'm catching for some very precious metal, or but this is my jewel actually. So this machine so far it worked for a small degree. Well, I think machine actually is a machine. You can implement to compute the program once you establish the technique, and you can implement it. So Xiao-Gang is actually very fantastic implementation of all these ideas. So I will mention more. So now let's look at some simple example. If I take an irreducible character of degree 3, 4, I think that this representation SL2 C1P is well known. So I just take it. Take the irreducible character of degree 3, degree 4, degree 5, degree 6. You put in the machine, you will get nothing. That means you won't have anything. Empty set. So if you take irreducible character of degree 2, well, there are 2 of them. I can tell you that I call it like chi1 and chi2. So what you get is 2 modular data. What are they? They actually, because some of you mentioned about Fibonacci here, this is Fibonacci modular tensor category, and they are Galois conjugate. One character give you 2, the other character give you another 2. But these 2 characters are also Galois conjugate. So end up you're getting a Galois conjugate irreducible character and a Galois conjugate of modular tensor category. They form a group, a collection together. So this is how I describe this as a machine, and these are all realizable modular category. So they are, I call it transitive because the underlying action of the Galois group is transitive, acting transitive on a simple object, and they are also classified by me and my collaborators. So I want to make this machine function better. So the input cannot be completely raw. I have to do some treatment before I process it. So there's something that remember that these representations are symmetric. So I realize that if you have a symmetric representation as an input, your job is a little easier, maybe a lot easier. So that's why we separate the topic with my student and postdoc. We basically say, okay, every character of SL2 CMOS NC is afforded by a symmetric representation. So you can always find a representative which is symmetric. So we prove it exists, actually we can construct it. So we go back all the way back to the number theories paper, Knopp and Morva. They use wave representation to construct all these irreducibles. So meanwhile, we produce the package which generates this symmetric representation. You give me the dimension, I can spell out all the irreducible, all the representation, all the symmetric representation, which cover all the characters of that dimension. It's bound. Maybe I should say something. If you bound the degree of the dimension, you will bound the level n. So you only have finitely many of them. So if you say I want to compute all the modular character, the character of any modular finite modular group of degree 5, they will spell out a bunch of them. So these are become like congruent representation, symmetric one, and it's finite. So So this package was constructed based on the result of Norman Morpha. So it's usually not studied by algebraists. All right. So why this is basically treatment, the initial treatment of the input. So this is basically the first one that we need. So if you start with a symmetric representation of SL2C, and which is equivalent to a modular data representation of SL2C, which is the one that is actually coming from a modular tensor category, efficient category, then you will find a real orthogonal matrix U which conjugate the raw one to a genuine one. And you commute with, you can assume these, the image of T are the same because it's just by permutation. These are diagonal. So therefore I just can assume they're the same and then assume they commute. So maybe this is the judgment why this is crucial. Well, it's not crucial at all if you look at mathematically. In fact, it's just a linear algebra exercise if I treat it as linear. But like if you computationally, you make a big difference. If you don't have this result, you end up getting like U rho S rho conjugate transpose, but this U is unitary instead of using orthogonal. Now if you commute, it also commute with this rho T, so U rho T, they're the same. So that means those, if you look at those distinct eigenvalue of rho T, then each of them will give you so U will be of this form in block form if you collect them together. And then you have this one, the block one, which is like, these are the complex number in the circle. So let's say this is a Z1, this is Z2. They are all complex number of linked one. Now what happened is these are continuous parameter. If you try to solve it, you get trouble there. So, but this one allows, if this is actually it's orthogonal, these number become plus or minus one. So you basically cut down a lot of unnecessary unknown that we don't know how to solve. So now, so because of that, we can actually implement. So otherwise we cannot implement it. So this is actually the initial processing of the data, and then we have a way to treat this raw material and then find out the outcome. I hope it makes sense. So now I basically use it as a starting point. I prime my input, and then I try to solve for, actually this is basically I solve for U now. If I get such a U, I'm done. If I don't have this U, I'm not done. But you can see it's the daunting task. I'm solving an unknown orthogonal matrix, which doesn't actually satisfy equation, just satisfy arithmetic rigidity. So this is the daunting task. So now, in fact, the example that I gave you was irreducible. So what if it's not irreducible? So they can decompose into a direct sum of irreducible. Then this is actually a very crucial one to prime it further. So if you can decompose a empty representation in two non-trivial components, their spectrum must overlap. So if you have if you decompose the representation into three irreducible factors, any division by two of them, their spectrum will be overlapped. So if you have three components, you have to satisfy the three spectrum relations. So this will eliminate another bunch of unnecessary, well, probably be sure they are not, that you cannot find anything in this kind of dirt. Yes?
What's the idea of why that's true?
It's because there's a row which is the dimension. The dimension play a role here. The dimension that all non-zero. So remember that I talked about S0I? It's a non-zero row. This non-zero play an important role. So if you don't know the dimension always non-zero, you cannot have this result. This comes from the non-zero dimension. So I did not elaborate any detail why it works. But I was thinking, like, if you're expert, then you probably have some idea what to. If you don't, then I just want to get you some impression of what I'm doing. Doesn't have to penetrate everywhere. So now let tell you how I can solve it. Theoretically, we can actually solve it for some situation. If you have well, maybe I should define the non-degeneracy. If I would say a representation non-degenerate, if rho t, well, if rho t. So remember, rho t is diagonal. So the if the eigenvalue does not have any multiplicity or all multiplicity 1, then we call this representation non-degenerate. That means all the eigenvalue of T matrix have multiplicity 1. So it won't have repeated eigenvalue. That's the underlying condition. So it worked for actually small degree irreducible. It followed from Wenzel's paper on Gray group actually. Degree 5, it all satisfies this. But when you higher degree, then may. But anyway, you can also look at the table. You can generate. So there are two conditions we can solve completely in this case. One is the intersection of these two spectrum has exactly one overlap, exactly one, and both of these representations have been degree bigger than 1. We can solve the S and T matrix directly, explicitly. The other situation is one spectrum contained in the other. This is basically the extreme case. This is something like the edge case. I can also solve it. So that means what I mean is I can use this modular data, assume it exists. I can write down the modular data without using even the machine, even use it by hand. That's what I meant here. Of course, you use the machine is probably more accurate than what I'm doing. So you would make mistake. Well, it doesn't mean it's limited to that. I just can write down a theorem for this. I can write down a theorem for more overlap. This is the problem. So let me tell you one example. I think it's an enlightened example. If you know what I'm talking here. So I take two irreducible. So I use this notation here. So maybe I just spend some time on this. So the first big one is the level, which is it's the dimension, degree. I call it degree. And the lowest subscript is the level. So a degree 4, level 7. The superscript 1 basically the Galois conjugate. I say 1 basically represents the Galois representative. I may take the representative Galois conjugate something else, but just take sake on this example. What about the second index? I can tensor with some linear character. So I put 0 there, I tensor the true. So it's just a notation. So then you ask the machine to generate, again, I get these two representation. And this is the first spectrum, and this is the second spectrum. So you can see that you look at these two spectrums, the overlap is just 1. So the overlap is 1. So that means I can solve it directly. So these gamma are just like cosine. But you can see the matrix, they don't sit inside the cyclotonic field. Well, the degree is 21, the level is 21 here, you combine. You can see the matrix has square root 2. So square root 2 only appear in level of multiple 8. So suddenly the solution that I'm going to solve is non-trivial. So but anyway, we can solve it. So end up we have this signs here. We come from these, as I said, we have some blocks. And there's some multiplicity of 1 eigenvalue. I get some signs. There was one thing I didn't tell you, which is the Frobenius-Perron dimension kick in. What is that? Which is a row in which, first of all, they are non-zero. They're all non-zero entries, and up to a scalar, they're all positive. This is actually it's not studied in VOAV. Only studied in modular tensor category. So you have such a row. This row could be overlapped with the unit object, but it could also separate. So if once you, because they have two rows, they only have like all the entries are non-zero. These are only possible unit row, and then I can use it. I can pick anyone to be the unit row. This is the way you get more than one modular data. I choose a different unit row. I get different modular data. So I get 2 of them. I get 2 modular data. So what is that? So now it can be completely solved. If you look at what we know about it, it's actually coming from the quantum group G2 level 3. So it's of level 21. So now then, okay, maybe I'm cheating right here. So no, I just completely coming from the representation that we generate from from the program. So the two possible choice give you two possible Galois conjugate of this quantum group G2 level 3. So it's an unusual way to construct modular data actually, coming from the representation. So this is a successful one. You can actually use a machine to give me something. Now I tell you some extreme now. This extreme is like a 3 component. Okay, if I say 3, 2, 1, degree 3, degree 2, degree 1, level 4, level 3, level 2. So you can see this is consistent with my previous notation here. Degree 3, level 4, and degree 2, level 3, degree 1, level 2. So you put it together using the generator of symmetric representation. And you realize that if you divide into this way, 3 and 3, then you can see that I have 2 overlaps. 1 negative 1, 1 negative 1. So it's different from what my statement presented before. So, but the problem is I can still solve it. I cannot write a theorem for it, but I can still solve it. So, both of them are non-degenerate. You can put it into one negative 1i, the other one is like 1/3 root and negative 1. Both of them are non-degenerate. So I can solve it. So in fact I can solve, you can see it's pretty precise. I can write down the solution. What is d? D is like 2 times the 3rd root, square root of 3 minus 3. So the complete S matrix is written down. Now it looks like a successful case. So you can see that I have 2 possible unit object again. So but once you figure out that you take any choice, just a permutation, you get the same modular data of the permutation. So okay, it looks like I get a successful one. No, there's one other thing. I can compute the fusion rule. Remember, if they are genuine modular data, I can go back to modular within the formula, compute the fusion rule. I did compute the fusion rule. Question? Okay. Yeah, you can compute the fusion rule. Then they are all non-negative integers. This you see, all of them are not. They satisfy all the properties that you need. It's pretty remarkable data. So one thing is, now we kick in, you need the associativity. So the associativity never show up in this case, but actually the one invariant which is captured the associativity, which is a higher indicator, higher Fibonacci indicator, that we studied with Peter Schoenberg. In fact, they're invariant of so-called the spherical fusion category. If it's modular, I have a formula like that. I usually call it Bante formula because Bante actually the first one to write this down for any group 2 without any proof. Anyway, so, but one thing is important. Yes?
Yeah, I have a question. So,
Sure.
maybe not understand. So the Berliner formula, right there, you're already assuming you have these
Yeah.
irreducible modules
Yeah.
for some conformal field theory.
Yeah.
So if you start with just the SL2s and you don't know there's conformal field theory.
You don't know.
Right, but suppose you can't, so in these cases, maybe you've got an answer that you can identify to one you already know.
Yeah, you can use
Okay,
VOA.
so if you don't know that it's there, can you recover a lattice and an orbital? Is there a potential?
If it's lattice, you can recover.
Right, if there's and so how do you, so suppose you start, you don't know there's a, where do you see the lattice that you can
Okay, if you see a lot of ones in the first row or unit row, or all ones, or plus or minus 1, so 1 or negative 1, this is actually lattice VOA.
Okay, and then you make a lattice. Can you recognize an orbital?
You can. Orbital is a lot harder.
I know, we need an orbital.
Orbital is a lot harder. I will mention about it.
No,
Orbital
I
is
just
something that.
understand what direction you're going in.
Yeah.
Okay.
I just this is, as I said, it's a machine. You put in the input. I want some output. This is the original, the very raw machine.
Yeah, I just wanted to understand where.
Yeah, it is exactly what you. I can only recover the model. I cannot recover the VOA because each model category are associated with infinitely many VOA.
But you can try to pick one. Yeah.
I can pick one. It's true. It's like an infinite fiber. I pick one.
Okay, very nice.
So I use the high indicator, but the second indicator is particularly important historically. They can only achieve the value 0, 1, and negative 1. So now I have all the data that I need to compute the second indicator. So I put it back to compute the second indicator. I get 2. Which means that whatever it works, there must be something fail, which is I think is associativity will fail. You cannot. I use the word categorification. The fusion rule cannot be categorified to a fusion category. That's what I try to allude to. So the second indicator basically tell you that this obstruction to living. Now I'm coming to the end. Yes.
Can you please repeat that? So you found compatible.
So
matrices?
you basically this guy gives you a fusion ring. It's a ring. It's you call it based ring in some context. You find a based ring. You want to categorify it. That means I want to find a fusion category which capture this fusion ring. You cannot. That's what I meant here. Because of the obstruction of the indicator. So now I just because we claim it because we are successfully identify all the rank 6. Basically all come from polynomial group. So it's disappointing because I don't find anything new. It's good I completely narrow it down. So you can look at both ways. These are all of them. And the representation type in terms of degree is completely break down in this way. Irreducible means 6, 4, 2 means that degree 4 type direct sum with degree 2. This is a decomposition of the modular data in terms of by using the irreducible, by using the lifting. So there's no new modular data. That's what I mean by disappointing. But maybe there's one point I want to point out. Actually, Xiao-Gang Wang is the first one who actually did this. He assumed the fusion ring has at most 3. He basically compute all of them using computer for the unitary modular data. So what we get today is all the Galois conjugate and this one. This one will never be all unitary or pseudo-unitary because they are negative dimensions. So, but it's fractional level. So the integral level they are good. Now, maybe I'm already over time a little, so maybe just wrap it up. If you look at this matrix I just pointed out, which is the failure one, the coefficient actually fall. That means like Xiao-Gang's previous result will never see this one. It will not. But afterwards it doesn't work. So of course with this machine will not stop at 6. We keep doing it, but this is the initial paper. We want to dump it out and see people like some disagreement. Say, I've done it before. Why don't you mention me? Whatever it is, I don't really care. I can add whatever name they want. So. But I want to point out when you go higher, you have something extreme. So classification rank 7 using this machine is pretty easy because 7 is a prime number. It's a short answer. Long answer is there's not many factorization, there are fewer choices. The non-integral ones start to be interesting. So you start, they either recognized by the quantum group, and the Lie group show up, which is a subfactor one. So how do you realize that? Basically, you take the Lie group, you're given by the Z5 with the parameter 5, and you double it in computer adjoint. You obtain it this way. So the Lie group of this parameterization exists. So therefore we are good to go. I guess for this one. The integral one actually is the first one, which is coming from d omega g, if you like, which is the orbital model of holomorphic VOA. So you see it in rank 8 actually. You don't see it in anything further, anything like below 8. Now go to the modular line. I put a red modular data here because I really don't know. So this is also the largest dimension that show up in the list. And it's like 336 plus 192, whatever number it is largest in terms of size. So we could show that, well, if I assume it exists, we could show that, again, it is the adjoint of the center of this Lie group of C3 parameter 6. Now the important thing is like this model is not known before. No literature and they don't have the double, whatever it is. So we just compute it in the other direction to recover. We go to rank 10, it's more heavy, the computation. And another extreme is 720 plus 320 times square root 5. If it's a genuine modular data, let me just use one word that probably never used in this lecture before, which is condensation. Whatever it means, you can condense it to so-called the pointed modular tensor case, which is like something coming from a lattice field array, let's say. And then you have only two project forms show up, which is either the free fermion, I use technical term, the other one is double over semion. So at this point, I close my talk. Thank you for your attention.
Any questions?
Yeah.
Has the Z3 6 new group been constructed just at the fusion category level? Categorification?
I think that the fusion category exists. I checked the literature. Z3, this one exists.
Is it new?
I forgot. I mean, I checked this one because I was worried about this whether this fusion category exists. This special parameter exists. I think I checked the literature, but the double never show up any literature. So they will never know what the data of the double look like. That's something I think maybe you may be interested. So maybe this affect people.
Any other questions or comments?
How do you know that your machine has stopped and you have found everything? What's like the stop?
Oh, we have to find everything because I enumerate all the representation of that degree. There won't be none of them will escape. What I cannot tell is the outcome. It's a general modular data. That means I have to go back to solve the pentagon.
Okay.
This is the part that nobody can do. Solving pentagon of modular of a fusion ring is like, if it's small rank, I think Ostrich did it for rank 2, maybe even for rank 3. Higher rank, I don't think is any, even you use computer, you have a problem solving the pentagon. Not a viable method, even using computer. Yes.
So do these new techniques in zesting play a role?
Zesting, I mean, like zesting, so my understanding of zesting is basically condensation. So you take a modular tensor category, you take another pointed one, or even, and then you tensor them, and then you start to condense the boson there. You basically, instead of like condensing the modular category by certain boson or algebra, you tensor with something that is not with opposite parity with the underlying with the anions, and then you form new boson there after you tensor them. Then you tensor, then you condense the boson in this tensor product. You get, I think it worked for almost all the time. But can I say? I think they have, but they have the zesting can apply to non-modular tensor category. So the fusion category. So that one I cannot recover from the other technique.
Any other comments or questions? If not, let's thank you for the